All right, so let's start going into some introductory material. Let me see if my fancy virtual pointer, I got this pointer because it gives me a little laser point that actually is in the video that's being recorded. So when you look at the video later on, you can actually see where I'm pointing, whereas you can't see that with a standard laser pointer. Okay, so before we begin solving quantum mechanical problems, you'll see if you looked at the very first sentence of Griffith's book, he basically just plunks down the Schrodinger equation and said, quantum mechanics is solving the Schrodinger equation, and that's really it. So let's just start getting into it. And the first, 2 or 3 chapters are all grinding through the problems you did in modern physics and a little bit more too, probably in much more detail than you saw them in modern physics. So just to address the background and connect it up with modern physics, I want to talk about some items on here. So we're going to start out talking about just some things we encountered in modern physics and just pull them together into a story. In other words, well, we're talking quantum mechanics, at least the version we're going to talk about, describes classical point particles, but in a quantum context. So the question you might start with is, what's wrong with classical point particles? Why can't we just build a world that's made of point particles and forces between them? And well, there's good reasons we'll talk about. Then we'll get into the differences between particles and waves. Quantum is going to be giving a wave description, and then the de Broglie hypothesis that matter has wave properties. And we'll continue on from there. I'm not going to talk about the other bullet items, but you'll see every once in a while I'm going to go back to this kind of these 5 things on here. We're going to work our way down the list in the first couple of days of class. And then once we have that background, we're going to introduce the Schrodinger equation. The last thing we talk about, I don't know if you talk about this, but where did the Schrodinger equation come from? Griffiths tells you nothing about it. Just it's a postulate, and in modern physics textbooks, I don't know, maybe your textbook is better than the one I have. It was the same, like, Schrodinger just postulated this equation, but there's logic behind where it comes from. So we'll talk about that right before we get to chapter 1 in Griffiths. Okay, so let's start with a discussion of what's wrong with classical point particles. Why can't we just have a theory? Or does it even make sense to make a theory where tables and crystals and things are made out of point particles that have forces between them? Presumably electric forces, right? I mean, that's the biggest, strongest force at sort of the nanoscale is the electrical force. That's going to be, gravity is really insignificant for electrons and protons, but electric forces are big. Okay, so here's a chunk of something, maybe salt, something like that, some crystal. How do you construct stable solid matter from classical particles? In other words, I want to put some particles, we're going to imagine they're point particles, adjacent to each other, and they're going to have forces between them to keep them from getting too close together and too far apart. And we want to make a crystal kind of out of it, at least in the simplest case. And that would be a model of what solid matter is. Okay, so how do we make something like this? And the usual picture that's shown, did I bring my little thing over? I guess I didn't. Most of you have seen probably from Dr. Neiser carrying we've got something that looks exactly like this. It's got springs between balls, right? And you can twist it and there's nice springy forces. I unfortunately left it in my office. And so those springs are standing in for forces. And the forces are making this piece of matter stable. In other words, there's a force that makes this atom not want to get any closer to this atom, a repulsive force. And then if it starts to stretch too far away, there's an attractive force. And we want to think about the nature of those repulsive and attractive forces. For us, again, it's pretty clear that if you're given the choice of the fundamental forces we know about, gravity is really weak. It's not going to hold anything together at this scale. And the other forces, the strong force, really goes to 0 at the separation between, an atomic lattice like this. The strong force, you have to be at nuclear distances for the strong force to really be significant. And the weak force, well, it's called the weak force. It's not going to do anything at this scale either. So electric forces are the only candidate forces. Electric and magnetic forces are the only candidate forces for holding this together. And, If we're talking about something that's essentially still here, we're not even going to have to think about magnetic forces because we don't have any moving charges, the sources of the magnetic field. So if we're talking about sodium chloride, maybe we've got some positive and negative sodium and chlorine ions there. And somehow through wishful thinking, I'm thinking, well, if I move this negative ion farther away from this positive ion, there's going to be an attractive force that pulls it back. And if it gets too close to this one, maybe the attractive force pulls it the other way. I don't know. It seems like it might work if you've never thought about it before. So how do electric forces hold this in a stable configuration? Let's think about it just step by step. Suppose I've got maybe a positive point charge Q. So I showed two of them in black, and I want to, let's imagine we pin those two charges down in space. So they're just fixed in space. And I want to place a third charge in the middle so we get a stable configuration. Now I might say, well, maybe I'll put a minus Q there. How immediately would I know that's not stable? I mean, it's going to be attracted to the ones on either side, right? So if it moves a little bit this way, if this is a minus Q I'm putting in the middle, if I move it a little bit this way, yes, this force gets stronger and the force with this one gets weaker. And so it's going to keep going in that direction and slam into the other one. That's not going to make a stable solid matter, right? So you might think, well, let's make it positive, right? Maybe if this is a 1 Coulomb charge, ridiculously large charge, 1 Coulomb, here's another 1 Coulomb. Well, they're all positive, right? And this doesn't want to get close to that one. It doesn't want to get close to that one. Hey, that seems kind of stable. Is it stable if I showed you that and we held it in the room here? Is it going to stay there? No, of course, it sneaks out the top or the bottom, right? This is not stable because if I move it just the tiniest bit in that direction, it keeps going. It wants to get away from those other positive charges. So that's not going to work. Uh-oh. This is always dangerous. I've got this fancy pointer. And when it does this, I can't remember how I get it out of this loop, but if I swing it around too fast and then unclick it, let's try it again. See if I, okay, good. I've had some situations. I have to remember when I push the button, I have to be deliberate about it and then move it kind of slowly and then deliberately unpush it. And I tend to wave it around like that and then let the button go. And it goes into this other mode where it starts moving things on the screen. Okay, so stable or unstable, clearly unstable. We tried both signs for that charge. It's not going to work either way. Well, okay, I can fix the top and the bottom. Let me put some other positive charges below it and above it. Is it stable or unstable then? Still unstable because it go in or out of the page, right? Okay, but we've only got 3 dimensions. So what about this situation? I've made a cube of positive charges, so 8 positive charges, and I put a charge at the very geometric center of the cube, same sign. Stable or unstable? Well, it looks like it would be stable. I mean, it seems like it's pinned in there, but I've got a lot of forces acting on this red one in the middle, and it's not exactly clear what is going to happen to it. It seems like, if I get close to one face, it's getting closer to those. If it's going to come out, if I bring it closer to this front face, it's going to get closer to all these positive charges, and wouldn't that push it back? It turns out that's not the case. Amazingly, this is an unstable configuration. In other words, if you put that charge right at the geometric center and then just push it a little bit towards the front face, it will keep going and leave the center of there, even though it doesn't seem like that. And there's a theorem, so that's unstable. There's a theorem that's not at all obvious, but you can prove it in electrostatics. It's called Earnshaw's theorem, at least restricted to charges, electrical charges. A collection of point charges cannot be maintained in a stable stationary equilibrium configuration solely by the electrostatic interaction of the charges. The more general statement of Earnshaw's theorem is it doesn't matter, it doesn't have to be electric forces, it's any 1 over r squared forces. So gravitational forces, you can't put a bunch of bodies with a combination of gravitational forces and electrical forces, they're not going to be stable. They're not going to want to sit there. Well, with gravity, we've only got one sign. So pretty clearly, if you put a bunch of planets around there and you just let them go, they're all crunched together. But it's not so clear for when you have opposite signs here. But Earnshaw's theorem says, no matter how clever you are, it's always going to be unstable. Same thing's true with magnetic forces. You know, magnetic forces are dipole forces, but they're still 1 over r squared forces. If you think about the Biot-Savart law, it's a 1 over r squared force. So there's no way, when I was an undergraduate, I probably shouldn't say, but I stole a bowl from the dining hall because I was, I was taking introductory physics, and I thought, well, wouldn't that be really cool? I'm going to make a floating ball with just magnets. So I bought a bunch of refrigerator magnets at the local hardware store or something like that. I took this bowl, which was just like a cereal bowl, and I glued all the magnets with the same pole facing inward to the bowl with just a hot glue gun. And then I took a ping pong ball, and I glued all the magnets with the same pole facing outward on it. And I thought, well, this is going to be really cool. I'm going to have a bowl with a floating ball in it, right? Because it's going to go down until those repelling north poles get close to each other, and then it's just going to float there. Why don't people make this? I mean, I'm going to be a millionaire. Well, it didn't work out so well. I mean, when I let it go, I built the whole thing and with my hot glue gun, and in a complicated way, it falls off the side and then sticks to the back side where the opposite sides are. There's no stable way. I thought it would be in the middle of this bowl and it would have to go up on the sides. The potential energy would increase as it went to one side. But that's not true. It was like it was at the top of a hill. I let it go and it fell off like that and stuck to the back side of the bowl. So it's true for magnetic forces too. That's neither here nor there for this argument. But the idea is, look, here's my idea for how to, here are my sodium ions. I'm going to put a chlorine ion there, and I want it to be stable under perturbations, and it's not stable. And Earnshaw's theorem is saying, no matter how creative you are, you're never going to be able to make stable matter. I don't know. I don't remember learning that when I was going through the intro courses. Now, it's far from clear that conceiving of matter as a kind of wave, as we're going to do in quantum mechanics, is going to help things at all, but it does. So at least we know this fails. We have some hope if we go to some sort of extended wave-like description, as we're going to be using in quantum mechanics. We're not point particles. Now we've got a wave function, some extended kind of thing. Okay, so that's kind of interesting. Solid matter is unstable. That's a big motivation. I'm not sure what people in the 1800s, who clearly had a good conception of what they thought matter was like, I'm sure there's been a thorough study of what the arguments were. They must have known that solid matter is unstable like that, and I'm not sure exactly what they were thinking was doing it. Maybe there's some other force that's not over a 1 over r squared force, but it's not clear what the candidate would be. If you tie strings or something like that, you can make it work, but a string isn't a 1 over r squared force that's action at a distance. Okay, not only is solid matter unstable, atoms are unstable. You heard this in quantum mechanics, in modern physics, right? So, even used to talk about this, and even in physics 110. What's the structure of an atom? So, I might say the simplest atom is a hydrogen atom. Here's an electron. Here's a proton, that's the nucleus in a hydrogen atom. And if the electron's attracted to the positive nucleus, why doesn't it just accelerate toward it and slam into it? This is what I might ask someone in physics 110, right? I'm trying to make an atom. So I took a proton and then I put an electron over here and I let it go and just slammed into it. That's never going to work, but that's not how we think of atoms as working if we're under the impression. So what has to happen? Yeah, the electron is orbiting, kind of like the moon orbits Earth or something, or Earth orbits sun. That's, if I release the moon from rest relative to Earth, it's just going to crash into Earth. But it keeps going around because as it gets attracted, it moves out of the way, and then it's attracted in a different direction. Same thing here. So the hope is we have some solar system model of the atom. Hopefully you talked about this in modern physics. There's a problem with that. And what is the problem? It's always what? It's always emitting electromagnetic radiation. In other words, anytime you have a charged particle, an electron is certainly charged. So we can imagine, the fiction that's almost true, that the protons rest in the middle, right? It doesn't do much wiggling because it's so massive compared to the electron. Anytime you take a charged particle and you wiggle it in any way, in other words, what matters is that you're accelerating it. If you accelerate a charged particle, it radiates some energy away. So if I take an electron here and I shake it back and forth in different ways, I'm accelerating it and energy is being lost. And that means my muscle is giving out energy and it's being lost as radiation going away. It's the same thing if something moves in a circle. Of course, that's a certain kind of radiation. And I had a little PhET simulation that I really love, but as far as I can see, it relies on flash. And flash has finally been completely gotten rid of. If you know the word flash, used to be a big thing, a way for showing animations, but flash is not supported by anyone. So I found this YouTube video. Let's see what's happening. And I'm telling myself I'm supposed to go to about 3 minutes here. So what there is, let me just pause this for a second. That little dot in the middle, the red one, is a positive charge. And what's going to happen now? So these little lines coming out of it are the field lines. And so if we go back to the beginning, you'll see it has the usual field lines, at least if you restrict them to 2 dimensions. Back here at the beginning, if I pause there, those are the field lines when it's not being accelerated. Now here someone's going to grab it and pull it to the side, and you'll see that stuff seems to wiggle outward radiatively. When you look at the field lines, you can see that the field lines are carrying something out, and that is sort of at least a visual indication that there's some sort of energy being carried away. So here's the thing moving in circular motion. Someone's pulling it in a circle. It's sort of a low quality animation, but you can see as someone drags this positive particle in a circle, well, the field lines make it look like some energy is being carried away, and it definitely is being carried away. And if this happens to an electron as it's orbiting a proton, if it loses energy, the only way that things can add up is if it goes to a lower potential energy, and that means it moves closer to the proton, and that means the atom's going to be unstable. So let's get back out of here and into here. So what it means is the electron is going to spiral into the nucleus in an amazingly short amount of time, 10 to the minus 11 seconds. And that's certainly not true. We have lots of atoms that are stable. So there's something wrong with that point particle picture that hopefully our wave model of things is going to patch up. That's not clear that it's going to patch it up right now, but at least we have some hope. And it's going to emit a continuum of electromagnetic radiation frequencies. We also know that, atoms, our stable atoms, don't emit ever continua of frequencies. They seem to emit just discrete frequencies. When we look at the spectra they emit. It's hard to see here. The lights are kind of bright in here, but what I've got is, I don't know, this is like a picture of the hydrogen spectral lines right there, right? So we take the line, any light coming out of hydrogen, and we separate it into wavelengths, and we'll see the typical spectral lines there. Same for all other atoms, mercury, helium, hydrogen, lithium. They all have their own spectral lines, but they're never a continuum. And so what are we going to do? And Bohr, I'll say, I was never that excited about the Bohr atom, but it really is revolutionary, right? I mean, that Bohr kind of looked and said, well, how much of classical physics can we hang on to? And then where exactly do I have to put the placeholders where you just have to hold your breath and say, I don't know what's going on, but I'm just going to make a rule that this is the way things are. Bohr said, well, at least for the hydrogen atom, matching up with the data we have for the spectral lines, I'm going to make a model of what an atom looks like. It's not clear when you see those spectral lines how we should even think of an atom. It's clearly not like a solar system, classical solar system. That picture is not working. So Bohr is just rebuilding it. He says there's a discrete set of circular electron orbits. He calls those stationary states. And they're defined by having integer multiples of h bar of orbital angular momentum. So this is the one H bar state, the 2 H bar state, the 3 H bar of angular momentum there. And those are certain kinds of electrons' orbits. And when the electron is in one of those stationary states, it just stays in those stationary states. It moves according to the classical mechanics, but it doesn't emit radiation for an unknown, unspecified reason. Bohr doesn't know why, but he says, you know, for some reason you get a free ride when you're on one of these orbits. Okay. The electron can't be in one of these intermediate states indefinitely, but what it can do is transition between, you know, say the n equals 4 stationary state and the n equals 2. And when it does, it emits a photon. It emits some radiation. And the radiation frequency corresponds to the energy difference between those two states. I know I'm telling you things you've heard many times before, right? So, you know, it may be in modern physics, you call the classical frequency nu. Is that more common in modern physics? So this would sort of, you know, if you rearrange things, put the H up there, this would say the energy of the photon corresponds to the change in energy between the two states. So E equals H nu. That sounds familiar to me, right? That's one of those quantum formulae for light. E equals H nu. Okay, and with that, Bohr predicts correctly the hydrogen lines, all of them, right? The ones that land on n equals 1 from higher states, n equals 2, and so on. All right, so he gets the hydrogen spectrum right, and there's clearly, I mean, that just is so much data right there for hydrogen. There's got to be some kind of truth in it, but it's clearly not the final theory. There's just too many placeholders in that theory. So the nagging question is why, and that's sort of the beginning of the quantum theory when Bohr puts those placeholders in there and at least has some partial success. Okay, so let's now, again, I apologize. This first few days is probably going to be more me talking at you. And we're not going to do like a super amount of problem solving, but it's just to remind you of the logic. Like, why are we even considering quantum mechanics? If somebody stops you on the street and asks you, why do people even talk about the strange theory of quantum mechanics? You could say, well, you know about point particles. It just won't work. Okay, so we're going to be talking about some kind of wave theory. That's a little bit vague right now. You know, Schrodinger's equation has wave-like solutions. So let's just compare particles as opposed to waves, okay? So what are some everyday examples of particles? Just throw a few out there.
Protons.
A proton. Very good, Alvis. An electron. A neutron. Okay, so all of you are sort of, you know, maybe we don't call them elements. Some of them are not considered elementary anymore, but they're part of elementary particle physics, right? They're all very small, almost point-like, right? We know neutrons aren't, you know, they're really composed of quarks now, but so we don't think of them as point-like anymore. They have some substructure. But, you know, occasionally people will use the word particle, not very often, as an extended body. You know, if I have a brick, it can move as a particle. And what that means is it's only translating. For some reason, when it's moving, it only translates, but it doesn't rotate. And it certainly doesn't compress or expand or deform in any weird way. Then it wouldn't be behaving like a particle. So a particle is something that really just translates. That's its only degree of freedom. It's so, if we have a point-like particle, there's no sense of it rotating, right? It can only rotate if it has some substructure, like a barbell diatomic molecule kind of shape. Then it can rotate. So when we say a particle, we usually think of something really small. How about a wave? What are some physical waves that we know about? Water waves, that's a great example. Sound waves, right? Those big ones, and electromagnetic radiation is a good example, but more complicated when you think about it because it has electric and magnetic fields involved. Okay, so let's just contrast the properties. Again, I apologize, this is all very straightforward stuff, you know. As someone on my dissertation committee told me when I was preparing a talk, never underestimate how much people like hearing something they already understand. The classic problem of graduate students is when they give a talk, they just immediately start talking over everyone's heads because they're afraid that everybody understands so much more than them. So, you know, it's always good to start from a common place. As an audience member, I really appreciate being able to go, oh yeah, I remember that. Okay, I'm on the same page as you. So properties of a particle. Well, so here's a bunch of particles being thrown at a nucleus at different impact parameters. Is that what that's called? How far you are from straight on to the nucleus. Here's one that's just sort of a grazing, it hardly gets deflected at all, but as closer you get to the nucleus, the more you might get bounced back. A particle stays localized. At any one time, it's at some position in space, and it travels along a definite path that you could parameterize by functions x of t, y of t, and z of t. Okay? We're not going to dwell on that too much because we're going to be talking about waves. What are the properties of waves that make them distinct from particles? So I'm picturing some water waves, surface water waves. They're not localized at all. In other words, if I say I'm thinking of a wave, this wave is spread all over the surface of this pool. I can't say where the wave is. It's kind of everywhere, at least that the medium extends. The medium here is the surface of the water. There's an amplitude at each point that changes with time, but there's no sense of a definite path, right? I would say as time goes on, this water wave is wiggling everywhere. It's not that it moves from here to there. Everywhere is just kind of wiggling and jiggling all over the pool. So that's really different than a particle. Okay? So sometimes people will make a statement. I had some more things in here, but I wasn't even sure what the questions I was asking. But when one says matter is particle-like, when I say, oh, here's some matter, it's particle-like. If someone said that, what might they mean? Yeah, certainly I could treat the whole table maybe as a particle if it just translated around. More often, I think people might be tempted to say, well, look, what person means, they should have been more precise. It's made of particles. If you really look closely, there's electrons and protons and neutrons in there, and they're all kind of like point particles. It's an ambiguous statement, but someone could be thinking either way. But when most people think of the word particle, they think of something kind of infinitely small, or at least very small. Even my kids in elementary school think of like, oh, it's down to the particle level. What if you could see an individual particle? If someone said matter is wave-like, what might that mean?
Electric flow or electric current.
Sorry, Alvis, did you say electric flow?
I suppose the more accurate word is electric current, but yes, essentially that idea.
Yeah, there could be a wave-like motion in electrons. Certainly, if you think of a wire, but we're really zoomed in, so the wire looks huge, like a pipe that could carry water. And I take the electron at this end and I move it quickly in that direction. Well, it's going to push on the adjacent electrons, but it's not going to instantaneously move the whole thing. I'll push down here and sort of a wave would go down of compression and relaxation as it propagated down, right? Because those electrons, I'm forcing them to get close to each other, but they don't like to be close to each other. So they push on the next one. And it takes a while to propagate down. But, people might think that, or more prosaically, they might just be thinking of water. Well, water can sort of be wave-like. Again, it's not a very precise use of language. If a physicist living before the discovery of quantum says matter is wave-like, they're probably thinking about a quantity of water or the sound waves in the room, and they might say, well, the air in the room is kind of wave-like. Well, it's not really wave-like. It's the medium for a wave. The wave is wave-like. The stuff it's made of is just the medium. That's not wavelength. The point I wanted to make here is that when a quantum physicist says that matter is wave-like, they don't mean anything like this first statement here. They mean that every single piece of what it's made of has its own wave-like properties. So the electrons, the protons, the neutrons, the subparticles of those, at least for the protons and the neutrons, are wave-like as well. So that's something rather revolutionary. Okay, I got to keep an eye on the time. 12:40. 12:40. Is this exactly off by 1 hour? 1:40. Okay, and we start at 12:40. We end at 1:40. So maybe that's a good stopping point right there before we start to go on and talk to light. So where we're going is we're going to talk about properties of matter, and people typically think of matter as being particle-like, at least in the classical way, and light well, Newton thought of it as being particle-like, but at least in the 1800s, it was accepted to be wave-like after Young's experiment, the Young double slit experiment. So we'll remind ourselves of those. And then we'll get to de Broglie, who flipped it on its head and said, not only can light be particle-like, but matter can be wave-like as well. All right, so I'm going to post what we went through today on the website on that right-hand side. And your only work before Wednesday is going to be, I think I asked you to do a little bit of the introductory reading. If you're having trouble seeing my website, send me an email and just tell me, you know, where you went to, or send me the link or whatever, or tell me what you're seeing. But just to do some reading, review these slides, tell me if you have any questions, and you're going to post those in the comment section. And I also asked you to read the first sections of Griffiths. We may not get there till Thursday or so, but just to give us a little bit of ahead of time stuff. Okay, anybody have other questions before we break? If you have other issues, just stay after. Otherwise,